Yeah, in this unit, we will be covering a good number of digital sensors or some smart sensors and their various applications. Like these digital sensors or smart sensors, already we have seen some examples in mobiles. How small they are and how intelligent they are. Basically, they have digital output. So though they don't require much of conditioning as such. Directly, they can be interfaced with the analog to digital converter, or in some cases, the digital output only is available. That's why the words smart or intelligent, these are the words used for them. Unlike the transducers or the self-generating sensors which we studied, they needed a lot of signal conditioning, and also in some cases analog to digital conversion or current to voltage conversion, or in some cases the reverse also. And we studied about some inverse transducers also, like piezoelectric or the inverse characteristic, basically the electrical to mechanical, mechanical to electrical. So these kind of sensors, or even the thermo EMF in case of thermocouples, where voltage to the difference of temperature to voltage, or the reverse. So these things were available and we could design suitable signal conditioning network and use them. In these digital sensors, as the name only says, the output is digital. In some cases, even if it is analog, built-in microcontrollers or microprocessors take the input signal, which is in analog form, and condition it and give it to the next stage. In some cases, even the analog to digital converter is also connected there, and that does the function of conversion, and this converted output can be utilized for the next stages. So like this, the digital or the smart sensors or the intelligent sensors which we are using are very useful in prototype building or in small day-to-day applications. And all these, they come with simple, say Arduino or Raspberry Pi, such small ones, and their range of applications are in good number. They cannot be used for longer time. So for longer time applications, you have to go for digital intelligent sensors with certain durability. And here we are going to cover good number of various digital sensors which can be used with microcontrollers or interfaced with directly microprocessors, or some of them already they have built-in ADCs with them. So with this introduction, we'll see in detail what are these digital and intelligent sensors. So these days we have good number of digital systems which can be available, which are available in affordable prices, and applications are in such a vast variety that all of us are tempted to use them for our applications. A simple, on our mobile we have a step count. So using that step count, you can select the alarms and how many kilometers you have walked. So your exercise routine also you can build around a simple sensor. It is a simple counter with the help of some geo-based sensor, position sensor. It is giving you this application. So here what I am trying to say is, sensor is sensing some specific parameter. Around that, around the same sensor, you can build a good number of applications. So using such overwhelming presence of digital systems for information processing and display in measurement and control systems makes these digital sensors very attractive. Because I gave example of simple position sensor. When the position is changed, a counter is set in, so the counter starts incrementing. So when the position of say 1 feet 2 feet out of them, 1 foot if it is connected to, then automatically every time the position is changed, so the counter is incremented. This counts the steps. So this is one of the ways in which a simple position sensor can be used. Similarly, the same position sensor can be used for many applications like this. In some, incremental types are there. What example I gave of foot count is incremental. Some of them are absolute position sensors. They have good number of applications in robots and all, where the exact position location, then later on lifting the object or keeping the object, all these things are associated with a simple position sensor. So around this, good number of applications can be built. So this is what is makes the digital sensors very attractive for usage. Since their output is directly in digital form, they require only very simple signal conditioning and are often less susceptible to electromagnetic interference than those analog sensors. So naturally, whatever is sensed is immediately converted to digital form. So there is no chance of spurious signals getting added. There is no possibility of electromagnetic interference happening with these signals, because the addition of the noise takes place in the different stages due to the different components used. It could be amplifier, it could be resistor, it could be capacitor, or even the lead wires also can generate the spurious noise signals due to drifts or any other additional parameters due to signal conditioning or the grounding effects or the reference voltage effects. So all these are possible because there is surrounding conditioning network involved in the sensing also. Whereas in case of digital sensors, whatever is sensed by the sensor is immediately converted into its digital equivalent. So these are not so much susceptible to electromagnetic interferences. The next point is 3 classes of digital sensors. Now, which are those 3 classes? Digital version of the measurand, that is the position encoders, where the digital version of the position is mentioned. The next one is relies on some physical oscillatory phenomenon that is later sensed by a conventional modulating or generating sensor. Now, what exactly here it is doing? Either some resonant mechanism, which usually in case of MRIs or CT scans is used, or variable frequencies are considered. So where the variation in the frequency or the counters, these are sensed, or quasi-digital sensors. So basically all of them lead to one simple sensor, that is a digital counter. All of them work on incremental counters. So the counters are associated with the sensing, and whenever there is some change observed, a counter is incremented. As a result of this, that oscillatory or the based on the counting, the results are recorded. So this is another way of digital sensing. Next one is digital sensors that use modulating sensors, including in variable electronic oscillators. These sensors do not require any ADC. Why they don't require any ADCs? Because already once they are given to a digital count, already the sensed parameter is converted in the digital form. So they don't require the conversion again. So these use modulating sensors. Even in the earlier self-generating type also, we have seen what are these modulating type. How exactly in the modulation technique, the errors are minimized, the offsets are reduced. Here also in the digital, whenever the modulating sensors are included, basically they are again taking help of the counting mechanism. So as a result of that, any variation is again given to a counter. So this afterwards, once the total count is taken, then it is converted, or the variation which is modulated in the form of the counts is again got back by demodulating it. So this type, naturally the errors are minimum here. That's why digital sensors are more popular. So first we'll see what is a position encoder. Now in position encoder, you have two types. One is incremental position encoder. The other one is absolute position encoder. Now incremental, the name itself says, it is giving you the incremented, say the tachometer, the speed. It is every time incremented and you are getting the incremented value. Similarly, our CD reader, optical CD reader. So basically here we are making use of an optical reader, and the tracks are incremented one after the other, whether it is reading from inside to outside or outside to in. The track numbers are incremented. Usually you might have seen the tracks are changed, then the numbers, song numbers are changed. So first thing, the outer track is taken in that position fixing. So here these are also incremental position encoder. And basically they take help of the digital counting mechanism, because here the concentric circles have to be located. If suppose 10 concentric circles are there here, and in each 10, what is the position? Say for the first one, if I give 0 as the first bit, then third position. So 0, 3 will be the count. On the 0th track, third position is my count. Like this, the digital counting, one for counting the number of tracks, one for counting the exact position. So like this, different counters are used so that the exact position can be located. So in this, what I mentioned, absolute means exactly it comes to a specific position, or incremental means slowly one after the other it is incremented and then you come to the position. Both have got their own advantages and disadvantages. So in this, we have one more class, that is linear and angular. Linear, what we have seen in our LVDT, where the linear positions are preferred to be measured. The displacements or the distance, such linear measurements are usually preferred in that LVDT type. In this concentric circular motions, the angular positions are located. So you have both the types of sensors. So linear and angular position sensors are the only type of digital output sensors that are available in several different commercial models. So basically here, using some laser beam, a exact position is located. For that, you may use the LED sensors or the position sensors, and that count is counted using a digital counter. Then the position is displayed. So incremental encoders are in fact quasi-digital. So here you make use of the incremental encoders, which basically they are not completely digital in nature, but they give the count in the digital form. So an incremental position encoder consists of a linear rule or a low inertia disk driven by part. So for this, you take example of our CD drive. So CD drive, you might have seen different concentric circles are there. This, when it is placed in our laptop, you have on top on the CD drive, there is a reader, which is optical reader. Once you enable that, the LED and the reading position plus the counters, all of them are initiated. And when you locate a specific location, this counter counts and the digital count accordingly is incremented and you get a specific reading. And always in angular position encoders, this is what happens. So an incremental position encoder consists of a linear rule or a low inertia disk driven by the part whose position is to be determined. That element includes two types of regions or sectors having a property that differentiates them, and these regions are arranged in repetitive pattern. That is what I said, no? One to locate the track, another one to locate the exact position. First you locate the track and then on that the exact position is located. So for locating the track, one counter is enabled, and to locate the exact position, like how many positions are covered, for that another count. So to locate the track, there is a LED which when it comes to that position, the digital counter is incremented. So like this, using two counters, you can arrive at the exact position you desire. So this is repetitive. Naturally, whenever you want to run the same tracks, it is repetitive process. And over again on the same tracks, it is being repeated. So here what happens? Sensing through a fixed head or reading device yield a definite output range. So for each position, the one pulse is generated. So for this pulse, digital counter is incremented. So a disk with a diameter d gives m pulses for each turn. Like this, you can fix how many pulses are going to be generated for a specific diameter. So on the basis of that, you can set the digital counter. So this is a simple concentric circle. So the circular formula applies here. The periphery divided by the number of divisions there. So that gives you the count. This sensing method is simple and economic but has following shortcomings. This is widely used, but what are the shortcomings of this? The information about the position is lost whenever power fails. That means it is stored in the RAM. So whenever there is a power failure, you have to reinitialize this. The entire process has to be reinitialized. These days, the softwares are being developed to go back to the old one and then start. In the older versions, you have this, but in the newer versions, you can see actually in the new softwares, you have start from where you stopped. That decision box you get. If you want to start from where you have stopped, you can always start from there. Usually you have the automatic power failures when they happen, restore the pages, restore your old pages. What it indicates? Basically this kind of a operation. Wherever you had stopped, from there you should begin again. You should not repeat the ones which you have already got information about. So just after switch on and also under strong interferences. Next point is, in order to obtain a digital output compatible with input-output peripherals in a computer, an up-down counter is necessary. This is a must. Whenever you are incrementing up counter, whenever you are decrementing down counter, these are a must. They do not detect the movement direction unless additional elements are added. So basically in all these counters, whether it is going up or down, this direction cannot be detected unless you have some magnetic field or electric field or optical field interfering with it. So the next type what you have is position encoder of another type. So that is magnetic type. See, in this you have optical encoders, magnetic encoders, or electric encoders, or electromagnetic type encoders as well, which are influenced by magneto-resistive type of basic sensor or that effect you have electric, magnetic, or optical encoders. In the CD drive, what example I gave, there I gave example of a optical position encoder. In the tachometer, you have the ferromagnetic field induced encoders. Tachometer is basically used for measuring the speed of the machine. The electric machine, induction machine, or a simple motor or generator, at what RPM the rotor is rotating. That in turn gives us the idea that at what speed how much voltage is getting generated if it is a generator. So to know that, the RPM, the revolutions per minute, that speed is to be measured. So in that case, the ferromagnetic or the magnetic field induced tachometers are used. These days, even the optical ones are also being used by sensing the position using a simple LED. It is being used. So here basically what is the design requirement is a toothed wheel or a etched metal tape associated with the scale of ferromagnetic material yields a voltage impulse every time it passes by a fixed coil. It is basically a magnetic field generation. Here you have where the cursor is pointing. This is the ferromagnetic wheel which is having tooth. Now this, when it comes in contact with this coil, there is this gap. So there is a magnetic field induced. Whenever this gap is there, the induced field is different. Whenever this tooth comes, the induced field is different. As a result of this, there is a variation in the field produced between these two. Due to this variation, for higher magnetic flux lines when they are cut, one pulse is generated, indicating the position of this tooth. And when air gap is coming, the flux lines in the voltage induced is different. By this, maintaining either a coil or a piece of magnet on which the coil is wound, by doing this, the magnetic field and the current flowing through them, you can have the position of the tooth and the air gap can be counted. So basically on the magnetic principle, magnetic induction principle, this is going to work. So this also is like a positional incrementer, what we saw in the earlier case with the optical light. So the resulting signal is almost sinusoidal, but it is easy to convert it into a square pulse. Naturally, for every peak of the sinusoid, if one pulse is generated, this can be very easily converted to pulses or digital count. So wave or determine its zero crossings. Anyway, either you count the positive peaks or you count the negative peaks, or you count the positive zero crossing or you count the negative zero crossing. Whichever you count, for every count, if you generate a pulse, easily this can be converted to pulses or square wave, and then you can count these pulses very easily using a digital counter. There is a minimal and a maximal velocity that determines the application range for this method, which is used, for example, in ABS, that is anti-lock braking system, which is widely used in all the vehicles, where the minimum and maximum speed limits are put, and this anti-lock braking system is widely used in most of the higher end cars. This has got a lot of advantages with speeds. That's why the ABS systems which are there in whichever vehicle, they cost definitely more because of the anti-lock braking system. Once it crosses that particular system, the brakes applied, they have some, like if you have studied this ECU of the car engines, you will know that how exactly the higher speed levels when they are going, this ABS system helps in managing it. And you have the airbags which once it crosses or once you apply that particular brake, how exactly these airbags are opened up and they help in preventing some accidents or the damages to the driver or the pillion rider. So this is magnetic based position encoder. So here you can see incremental position encoder, again on the principle of the magnetic, where you have these two, where the input is coming and input is always sinusoidal, which through the coil, and because of this the position 0 where the air and the tooth, so different positions can be identified by the flux lines cut by these particular magnetic lines or the magnetic field which is developed. So in this figure shows another inductive system, but this time based on a toroid with two windings. So here the number of windings are fixed, and how much this again same magnetic field is induced in these due to the air gap or due to the tooth, it is measured. So one winding is used for exciting using currents between 20 kilohertz and 2 kilohertz, and the other one is used for detection. Here you have two windings, one for exciting these coils and another one for studying the change that is happening in these windings or these flux lines. So the same principle can be used in a different way for sensing and generating these position encoders. And all these are dependent on what is going to be the size requirement of your sensor plus what is going to be the application range. On the basis of that, the same principle, either using toroids or simple coil winding in the earlier case what we saw, or using a simple coil wound on a piece of ferromagnetic material. All these things are one and the same, only thing depending upon the application, you have different varieties in there. So there are two output stages, one when no voltage is detected and 0 when there is some voltage detected. Again, another way is glass technology in incremental position encoders. Now, what is this glass technology? Here, in the glass technology,